So in this section, we're talking about, well, we're just calling them the T procedures, but really they're called the one sample T procedures, where we're assuming that we have a single population and we're trying to figure out the information about that population mean by using our sample mean. There are procedures called the two sample T procedures where we can compare means from two different populations. We compare two different sample means from different groups, which are good for experiments, comparison studies. And it says here it's more common in the real world to do experiments and do comparison studies instead of looking at a single mean. But there's one type of experimental study where we can actually use these same procedures, and that's matched pairs. When you do matched pairs, you either have the same individuals receiving multiple treatments, or somehow you've been able to pair up the participants. Sometimes in medical studies they might use identical twins or something. But you have these individuals that you can pair up, and then you can compare the means that you get or the values that you get there, and you do a hypothesis test on the differences. So you find the differences between the two sets of data because they're paired up, and then you can run a single sample t-test on the differences. So let's look at an example of this. Okay? So this would be good for something like a taste test. So suppose you have a random sample of 10 adults that are participating in a taste test experiment, and it's a blind taste test. So you blindfold them, and you even use some, probably in real life would use some randomization as to whether you give them which particular soda first. If we have just, let's say we have sodas A and B, to not name any commercial products, but you might give half the people soda A first and then soda B, and then the others soda B and then soda A, kind of randomly deciding if you wanted everything to be completely blind and as random as you could make it. But anyway, you have 10 people, and each one is sampling each of the two sodas, and then they're going to rate them from 1 to 5, where a 1 is the worst and a 5 is the best. And so we have the data here. And so we want to do a hypothesis test and figure out, do they like one better than the other? And we're going to base it on this here. Is there significant evidence at alpha equals 0.05 that adults prefer soda B? Okay. So first of all, we're going to look at the differences. And you could do soda B minus soda A or soda A minus soda B. You just have to be careful with your alternate hypothesis based on what you're trying to show over here, okay, or trying to test over here. So if we do soda B minus soda A, my null hypothesis, and this is always the case when you do the matched pairs like this. I mean, I guess you could compare to a different value, but like 99% of the time, in most cases I've ever seen, for the matched pairs, you got mu equals 0, okay, because you were looking for no difference there, that there's no difference in their preference of soda A and soda B. So mu is representing the average of the differences. Okay, we'll get an x bar, which is the average for these 10 people. Mu would be the average difference for the entire population. And the alternative, since we did soda B minus soda A, if they prefer soda B, then those values would be larger than the soda A values, and these would come out to be positive. So our alternative would be that mu is positive, greater than 0. Okay, if we'd done soda A minus soda B, it would switch the inequality sign based on this hypothesis. But if we did soda B minus soda A and we think they're going to prefer soda B in our alternative hypothesis, we'd have greater than 0. And then we just run the one sample test there. I went ahead and computed x bar to be 0.7 and s to be 1.1595, and I showed a few more of the details. Let's suppose you didn't want to use the t-test. You wanted to go through the t-statistic and the probability that way. Well, you could compute directly. The t-statistic is your x bar minus mu from the hypothesis, from the null hypothesis, which is 0, and then divide that by the sample standard deviation over square root of the sample size. Sample size was 10. And so we get 0.7 divided by the quantity, 1.1595 over square root of 10, and you wind up with the test statistic of 1.91 if you round it off. It's a one sample test. It would be an upper tail because you have the greater than, so there's actually a TCDF on the calculator, or you could look it up in a table of values if you didn't have a calculator that can do this. But you can do the T cumulative density function, and you would have a lower bound of your test statistic here, 1.91, and then an upper bound of infinity, or on our calculator we can do 1e99 for 1 and 99 zeros. 1 times 10 to the 99th is what that represents. And then you give it the degrees of freedom. Remember, on the normal CDF, the last two arguments were mu and sigma. Here you don't give it a mu and sigma, you give it degrees of freedom. And it turns out to be about 0.04, about 4%. And I got some screenshots if you were to do it the other way. So you enter your data into a list. You'd have 10 values, And you could go and do a t-test, which is basically what I've done there at the bottom by computing the test statistic and the probability. That's exactly what the t-test does for you if you use the calculator. So you could, if you entered the data in, you select data, and let me back up for a second. Select the data, put the null hypothesis that it's equal to 0. The data's in L1, leave frequency at 1 if we're not using frequency lists. And then from the alternative hypothesis, we're going with greater than 0, greater than mu sub 0. And then you calculate or draw, and you'll get exactly the values I have here. The test statistic, t, is 1.91 if you round it, and p is 0.044. And then your conclusion at alpha equals 0.05, we have significant evidence to reject the null hypothesis and conclude that yes, they prefer soda B. Okay? Yes, there is significant evidence that adults prefer soda B if this is truly a random sample. And then the last thing that I want to say is the T procedures are quite robust, what we call robust, which means that if you don't meet all of the assumptions, they're still relatively accurate in certain cases. We say a procedure is robust if when you have some small deviations from the assumptions that you still get fairly accurate results. You have to have random sampling, okay? But in particular, your sample size, because of the central limit theorem, here we're using S instead of sigma, but large samples help smooth out the distributions, the sampling distribution. So if you have small samples, say less than 15 or so, you still need to have relatively normal distribution. You might check the regression plot that I showed you. But if you get large, say you get larger than 40 or so, then you can even handle strong skew and still use the t-distributions. So the t-distributions are extremely robust if you use large enough sample sizes.